Okay, all right. Let me just start recording. All right. So what have you guys decided regarding the term and examination? Can you hear me?
So we didn't have a class discussion on that. We thought it was decided on that day.
It was decided on?
In the last class, we thought it was discussed in the last class. We didn't have any discussion on our class group.
Okay, but I remember that you asked for time, right? Regarding whether you want it to be a pen and paper and R test?
Sorry, sir, we didn't have a discussion on that.
Okay, all right. So can we just finalize it now? Because
most of the AFE people are wanting it to be R. I don't know about MSc.
Come again, most of?
AFE are wanting it to be R, like financial economics, but I don't know about MSc economics, the other batch.
Okay, all right. What would you say too?
Sir, I think most of them will have reference towards R, but like as I said, we didn't have any discussion. If anyone has a problem with R, can say right now.
Okay, yeah. So assuming that you don't have any problem on R, if someone has, please raise an issue right now. Otherwise, your term and examination will be on R. If there is any issue, please let me know right now so that it can be addressed. No, right? So shall I safely assume that R will be preferable?
Yes, sir.
Okay, all right.
So
yeah.
Like I have some query in regarding like basically we don't have like in various that coding and all. So we like you just send us that whole console and R file and all, but in some particular this we have some problem. So like could you please send us or tell us how to do something in like basically an organized set of things so that we could have some knowledge about before exam. Whole thing.
I exactly do not get what you want from me, Mohit.
So exactly, I want an organized like whole material, sir, so that we can apply this or practice these things.
Okay, so all the class recordings are there, right, on Google Drive?
Yes, sir, that we have. But in some like in class, you just told us you will send some code to us and we will practice that code. So in that code, I think we have some problem.
Okay.
Sir, we can also solve it from Woolbridge, na? Like it has many different examples.
Yeah. So mainly we have what we have
solved. Sir, you said you would share dummy variable and all, but you didn't share. So
I will.
Okay.
I will. Don't worry. So, so I'll see if I can send you some of the organized R file in the sense that, you know, starting from how do we actually assign vectors and taking some examples from linear regression model so that it can be a complementary.
Basically, just solve one or two examples properly in R and share with us, like which has everything.
Oh, okay. That I'll do.
Sir?
Yeah.
Sir, will third periodic will be an R test or a pen paper?
Mostly let it be on R only. And
okay, sir.
Yeah. So when is your third periodical?
So next
30th. 30th of this month.
30th, right? So guys, after 30th, your classes are supposed to end, right?
Yes, sir. 38th is the last day.
And
actually 29th is the last day.
And when is your final sem starting?
So
And
12.
right, sir? 12.
ओके सो 30th से 12th के बीच में क्या हम 2-3 सेशन के लिए मिल सकते हैं?
So between when?
30th to 12th जब से आपका एग्जाम शुरू होता है और 30th के बाद.
So I personally would not mind, but I can't speak for the class.
Okay, what about others?
It can work, sir.
है ना, सेमेस्टर एग्जामिनेशन है गाइस, जितना हम कवर कर लेंगे अभी उतना बेटर है. आपको आगे प्लेसमेंट या इंटरव्यूज में वो ज्यादा हेल्पफुल होगा.
सर टाइम सीरीज कराओगे ना उस वक्त, लेकिन मतलब
जो भी होगा टाइम सीरीज, साइमल्टेनियस इक्वेशन, जितना हम कवर कर सकते हैं एटलीस्ट अच्छे से. सो
बट सेशन एक्सटेंड मत करना सर, लाइक 2 घंटे के पर डे, क्योंकि कभी कभी होता है सर 4-4 5-5 घंटे के एक सेशन हो जाते हैं.
बट ठीक है, 30th के बाद तो ऐसे कोई क्लासेस नहीं होंगे ना आपके?
पता नहीं सर बाकी टीचर्स का.
Like we don't know whether other teachers will take or not. That's the thing.
Okay, all right.
We might have some class.
Okay.
Yes, sir.
Yeah.
So for MSc Economics, actually our 2 courses are lagging behind, like the syllabus has not been covered. That is Economic Growth and Development and Monetary Macroeconomics. So both of them are like, it might happen that we'll have extra classes, and even for microeconomics we might have extra classes. So our syllabus is way behind than any course for many subjects. So if you are willing to take class, I think nobody will have a problem. But if you cannot include that in the end STEM exam, then that will be better, because after learning, then again revising that and then giving the exam will be a problem.
एक चीज I can guarantee that whatever classes that we'll have, it will just increase your concepts only. So whether it is tested or not, don't worry for that. Because you have to understand that mostly what we'll do is, these practice exercises on some of the interview questions that you might get asked, because after your second semester, third semester starts with the worrying phase of placements. So mostly as an econometrics faculty, I would want all of you to be absolutely prepared for at least the basic interview questions that are asked. So रही बात जहाँ तक term end examination में आने की, so mostly we'll try to cover all the portions before, मतलब till 30th, और उसके बाद जो भी होगा, we can think of this as a revision for ourselves in future. So that's why I'm saying that it should not be a problem. Just treat all those extra classes as a learning and revision. ठीक है?
Okay.
Yes, sir, that will be fine.
As a faculty, I am responsible for your basic knowledge, basic concepts as far as econometrics is concerned. So that's why I personally want to do it. Otherwise, till 30th, you see, whatever the syllabus gets covered, we are fine with that. All right. So let us move ahead and try and discuss new concepts today, which is...
And so what will be the syllabus for periodicals? Would it be till today? Like...
ठीक है, till today, let us finalize the syllabus for periodical 3. ठीक है?
Okay, sir.
Okay, all right. ठीक है, shall I start then?
Yes, sir.
Okay, all right. So let us start our discussion on time series, because once you go to the next semester course, if whether it is for financial guys or for MSc Economics guys, financial guys it will be financial econometrics, and for MSc people it will be advanced econometrics. So mostly what you learn there will be an extension of time series in full detail. So what we'll do, what our intention will be in this course is to cover the basic aspects of time series and just learn something, before handling or before talking about time series. What are the basic things that, is required on part of us researchers or learners. So before that, I like to talk about these are three major sources of data points that as a researcher we have. So to conduct any regression analysis, or for that matter any econometric analysis, you need data. And there are generally three types of data that are mainly available for analysis. Can you all see the screen?
Yes.
sir.
Yeah. So the three types of data that we often come across as a researcher is, your cross-sectional analysis, cross-sectional data, sorry. Then you have time series data. And then you have pooled or panel data. So till now, whatever we have discussed, mostly they have all pertained to cross-sectional data. And by cross-sectional data, what we exactly mean is that these are data collected on one or more variables, but they are collected at the same point in time. So, if you're talking about income of or income data collected for a given locality. So what you're doing is you're collecting income as a variable for, let's say, 300, 400 sample at one particular point in time. So cross-section means you're talking about collection of data on variables, whether it is one or more than one variable, and they are all collected at the same point in time. Meaning which जो observation, जो row होता है आपका data frame में, they all pertain to the sample of your data matrix. So if you have, let's say, 5 number of variables: income, education, marital status, age, sex, and then you have, let's say, 3, you collect information on all these 5 variables for, let's say, 500 or 600 or 1000 individuals. So this is an example of a cross-sectional data that we should understand. One of the very famous example of cross-sectional data will also be the census data that is done every 10 years as far as Indian economy is concerned. But mostly in cross-sectional data, one of the assumption of CLRM that we have regarding homogeneous, or you can say homoscedastic variance of error term. Most often this assumption of homogeneity or homoscedasticity in variances gets violated. So often cross-sectional data comes with the problem of what is called as heterogeneity. So heterogeneity, mostly it tells you that the variances of the error terms condition the data matrix, which is assumed to be constant as far as the assumption of CLRM or ordinary least square method. This assumption mostly get violated when you have cross-sectional data, because what it says is that variances of the error term condition the data matrix should remain constant ideally, but when you have variables collected, or the data or information on variables collected at the same point in time across different sections, that's why it is called cross sections. Also, it is not necessarily true that variances of the error term will be constant across all the different sections of the given population or the sample. So cross-sectional data often comes or often presents the problem of what is called as heterogeneity, which is what we had discussed when we were talking about heteroscedasticity. That is when you have violation of assumptions of homoscedasticity. Then comes your time series data. It automatically it says that these are the observation or a set of observations that a variable takes at a different point of time. You can have many examples, and financial data are often mostly an example of time series data, where you have stock prices or whether you're talking about macroeconomic variables like money supply or unemployment rate or CPI or GDP. So all such data where you have a set of observations that a variable, a single variable or more than one variable takes at different points of time. So in the time series data, what you have is the rows of the data matrix, that is these rows of the data matrix, these are the different points of time on which the information on the variables have been collected. So if you're talking about annual GDP of India from, let's say, 1950 to 2010, and since you're talking about annual GDP, so here you have precisely 61 data points. So what it gives you is that the information collected on the variable, where the variable here is my gross domestic product. So I have an information on the variable for the year 1950, 1951, 52, and so on till 2010. So such kind of data set are an example of a time series. You can also have daily stock prices. You can also have quarterly GDP data. You can also have, let's say, monthly inflation data, that is CPI data. So basically a time series is a set of observations that a variable will take at different times. So if you're just thinking in terms of the data frame or the data matrix that we have, so the row of the data will tell you or gives information on the variables at different points of time. Now mostly as far as our course or course at postgraduate level is concerned, mostly what we deal with is called as discrete time series, which will just discrete time series data, which we'll just talk about in few moments from now. So discrete time series data basically क्या होता है, when you have set of these observations collected at different points of time, all these observations are equally spaced. Now, what do I mean by equally spaced is, so suppose here the example that we had just talked about, that I have the GDP data of India from 1950 to 2010, and this I call it as annual data. So if I just refer to 1950 data point as Y0, then next data will be Y1, Y2, and so on and so forth. But what you notice is that the difference between, or the space of interval between Y0 and Y1 is 1, Y1 and Y2 is 1, Y2 and Y3 is 1, where this 1 is referred to as year. Similarly, I can have daily stock price data. So if if you have an information on stock prices of, let's say, Reliance for past 1 year, assuming that the data is also available for weekends and all the other days. So what is happening over here is that all your data points are equally spaced. Equally spaced means I have the data on day 1, day 2, day 3. So all these data points are separated by the unit, which is here day. Similarly, when you have monthly data, in that case, the difference between the data points is that of 1 month. So when you have a set of observations collected on variable where they are equally spaced across time, such data points are called as discrete data points. And they are also an example of what is called a discrete time series. On the other hand, when you have data collected on or collected across time where time interval is not equally spaced, something like you can take examples of readings on electrocardiogram, where these data points are continuously monitored or continuously obtained. So in that case, the time period of one observation with the other observation is not equally spaced. Similarly, you can think of examples of stock prices data where the stock markets are not operational on the weekends. So in that case, what happens is let's say data point on Friday and the data point on Monday, they are separated by 2 days. So when you have an example, when you have a data set or collection of variables across points of time which are not equally spaced, which do not have equal intervals, such type of data points are called as non-discrete or continuous time series observation. Most of the time for our course, what we'll be talking about is discrete time series process. Then you have the last section, which is called your pooled data or also panel data. So pooled data or panel data is exactly a combination which features both cross-section and time series data. Now, for example, you have GDP data for past 50 years for 50 countries. So what case I have here is, I have a variable, let us call this variable as Y. I have sections, let us call that section as I. So I is equal to 1 for India, I is equal to 2 for US, I is equal to 3 for Canada, and so on and so forth. So in that case, let's say you have I, going from 1 to 50, where it just tells you that you have information about these 50 countries on the GDP values. And then you have such information for, let's say, 10 years, 20 years, 30 years. So your panel observations, they will be denoted by this double subscript where, they can be thought to be written as YIT. So if you're, let's say, if you're talking about GDP data of US and India for, let's say, 1970 and 1971. So how will your panel look like? You will have GDP data, so you'll have US data. You'll have 1970s US GDP, 1971 US GDP. Then you'll have India data. You'll have 1970 GDP of India, 1971 GDP of India. So combination of cross-sectional information and time series observation is nothing but called as pooled data or panel data. So, and in econometrics, many times, or in social science research, many times we face such kind of data where we have to, in order to apply linear regression or regression techniques, some of the techniques which are specifically used in order to analyze the panel data. That's where you have random effect and random model and fixed effect model. And there are other methods also to talk about the panel data analysis. But panel data typically consists of observations, or you can say values of variable across different sections and for as many time periods as you have the data points. So basically, these are the three sources of data points that a researcher comes across when he or she talks about regression analysis. So you have cross-sectional data where you have information on a variable across different sections of the population. You have a time series data where you have a set of observations collected at different points in time. And then finally, you have panel data where you have information on cross sections about a variable for different points in time. All right, so let us move ahead and try and discuss what exactly we want to discuss as far as time series is concerned.
Sir, I have a question.
Yeah.
Sir, it may be confusing a bit for me, but I wanted to ask. Sir, won't the autocollinearity assumption be violated sometimes in time series?
Definitely. So one of the major assumption of CLRM gets violated in time series, and that's why the time series models that are mainly estimated they are estimated using different methods, because most of the time in the time series, like in cross sections, we have the problem of violation of homoscedasticity. For time series, we'll have the problem of autocorrelation, which is what we'll discuss as we go ahead and talk about time series. All right, so let us talk about time series, what exactly we mean by time series. And so let me ask if any one of you can answer what exactly we understand by time series observation.
Data collected on a variable over a different interval of time.
Correct. And so we just talked about that the time series points, or the time series model that mostly we discuss as far as our course is concerned. We'll mostly talk about the discrete time series process, where the discrete time series process is the set of observations collected on a variable across time period, but all of them are equally spaced. So such kind of observations, such kind of set of observations collected on a variable, they are called as discrete time series. So let us try and understand what exactly we mean by this. So mostly what we understand that we have a variable, let us call that variable y, and that variable is a function of time. So if you have a quarterly GDP data, or if you have monthly money supply data, or quarterly or monthly inflation data, yearly GDP data. So what we understand that the variable y, that random variable y, is a function of time. So at a specific value t star, y takes on a specific value. So formally we can write it as yt star is the value that it takes at value t star. Similarly, if we go ahead in time, let us say, we move from t star to t star plus h. So what it says is that at t star plus h, what will be the value that y takes? So y at t star plus h will be a function which it takes at this specific value t star plus h. So what we notice here is now this h which separates yt star and yt star plus h, this h is called your interval. And by the discrete time series, what we understand, or what we are saying here is that this h represents a unit change. Now, whether you're talking about daily change or annual, yearly change or quarterly change or monthly change, it does not matter. What matters is that this h is normalized and equal to 1. So if I have, let's say, yearly data, I'll have y1, y2, y3, and so on and so forth. So you understand that this y1, y2, they are separated by 1 year. y2, y3, they are separated by 1 year, and so on and so forth. So this h, which separates the value of the variable which it takes at two different or two distinct point of time, is normalized and equal to 1. What it, or how it should be interpreted is that this h represents a unit change in t. And then when you consider such kind of sequence, this sequence will be of equally spaced values of this y. So when we have such cases, so y1, y2, y3, so on and so forth, it can also be thought of as yt plus h, yt plus 2h, yt plus 3h, and so on and so forth, where h is equal to 1. So automatically you get all these equally spaced values of the independent variable, in this case is y. And when we have such cases, we can easily define the first differences, which are written as del y t, and this can be thought of as f of t minus of f of t minus 1, which can automatically be simply written as yt minus yt minus 1. So this is called your first difference. What are you doing? You're simply taking the raw observations, which are equally spaced values, and then you are obtaining a new series, and the series, how you obtain that series? You subtract each of the current observations from its previous observation. So if in the original series you have 5 observations, you automatically understand that in the first difference series you will have 4 observations, and so on and so forth. Similarly, if I want to talk about del y t plus 1, it must be equal to f of t plus 1 minus of f of t, and this will be simply written as yt plus 1 minus yt. And you can easily calculate del y plus t plus 2. So it will be f of t plus 2 minus of f of t plus 1, and which can be written as yt plus 2 minus yt plus 1.
Sir?
Yeah.
One more. Sir, is it necessary that the time series data should be uniformly spaced, or what problem will happen if it is not uniformly spaced?
No, it is not. That's why I'm saying it is not necessarily, but as far as our course will be concerned, we'll be mostly dealing with the time series which are equally and uniformly spaced. So for ununiform spaced observations, we have different methods where we use the concept of differential equation, which is what will not dwell as far as our course is concerned. We'll be mostly talking about the time series observations which are equally spaced. So in this case, in this sense, you can easily verify that, you know, I can write this whole sequence. Let's say starting with yt, I can have yt plus 1 and so on and so forth. Similarly, I'll have yt minus 1, yt minus 2 and so on and so forth. And it can go take on infinite values. That is, this t with index, it can run from minus infinity to plus infinity. So such sequence of observations on independent variable which are equally spaced, they are an example of discrete time series. So all the models, all the theoretical models, even and the models that are actually estimated for such kind of discrete time series variables, they are nothing but finding a solution to what is called as difference equation. Whereas difference equation in its most general form is a equation which mostly let me talk about in this manner. So when you have observations which are equally spaced across time, what essentially we are dealing with is called difference equation. When you have observations which are continuous across time, what we talk about are, they are called as differential equation. Now, while in macroeconomics, when we are talking about, you know, the various theoretical models, whether it's Ramsey model or Diamond's model, what we are mainly talking about is the solution to differential equation, because what we had in front of us is the variables which are linked across time in a continuous fashion. So whereas when we have the discrete process, in the discrete process, what we have is that it does not matter whether the variable in front of us is continuous or discrete. What matters is that the values of the variable or the information on the variable that we have in front of us, they are separated by an equally spaced time. So I can write yt as some function of yt minus 1 or some function of yt minus 2 and so on and so forth. And we can easily find solution to such kind of equations which are called as solution to difference equation. But when you have uniform variations, or you can say, when you have continuous changes in time or when you have observations recorded on the variable which are continuous in time, that's where you are talking about solutions to differential equation. And that's what the difference between difference equation and differential equation is. So you can think of that in its most general form, a difference equation, it expresses the value of a variable. In its most general form, difference equation expresses the value of a variable as a function of its own lagged values, time, and other exogenous variable. This is what generally a difference equation looks like. So you can have a difference equation which looks like yt is a function of, let's say, 1 plus 0.1 times t. This is an example of a difference equation because what we have is I have a variable y which is expressed as a function of time. Or I can also have a variable y which can be written as, let's say, beta naught plus beta 1 times yt minus 1. Or I can also have a combination of such things. So mostly what we talk about as far as the course on time series is concerned is an example of difference equation. And in all probability, the simplest difference equation that we talk about is called as linear difference equation. So what do we exactly mean by linear difference equation? Let us try and understand that. So since I have maintained that we'll be talking about linear time series models, whereby linear time series models is that mainly we are talking about all those variables which are equally spaced or discrete time series. So all the examples that mostly we come across or mostly we'll solve, they will all be an example of a special nth ordered linear difference equation. And the functional form of that equation goes as just don't worry guys, in notation hai sirf once I expand this you'll automatically understand that what I'm talking about. So in its most general form, all the models that we study in time series, they are all an example of this nth order linear difference equation. I'll explain all these terms one by one. What do I mean by nth order linear difference equation? You simply expand this, and just for the time being, just ignore this xt term over here, just for the time being. So assuming this xt not here, if let's say I tell you that I is equal to 2, how do I, or let's say just simply let us start with I is equal to 1. How do I write this as yt as a naught plus a1 yt minus 1. If I take I goes from 1 to 2, it will be a2 yt minus 2. And similarly, if I keep on expanding till nth term, I have this term. Now you see what essentially we get here is, what we are seeing in this equation is that y, or current value of the independent variable that we have in front of us, yt, is a function of its one period lag, yt minus 1. So ये सारे observations are already collected by you. So if I have the annual GDP, and if let's say I'm saying that GDP of India at 2010, so let us understand that this is GDP 2010, and if I let's say saying that this is my original equation, what I'm saying that the GDP of 2010 can easily be calculated or estimated by this equation, where I say that the current value of GDP depends on one period lag value of GDP, that is GDP of 2009, and two period lag values of GDP, that is GDP of 2008. And if you have n number of such terms, what it means is that the current value of GDP depends on its n previous lagged observation. And these A0, A1, A2, and so on and so forth, they all are linear coefficients. So this linear gives the term linear. Difference equation is because the difference equation is expression of an independent variable as a function of its lag. That's why it's a difference equation. Now, nth order means the n lags that I'm talking about. So if you go to 2 lag, it will be second order linear difference equation. If you go to 3 lag, it will be third order linear difference equation. And if you go to n lags, it will be nth order linear difference equation. And this also has got a very beautiful name, and I'm sure that all of you are familiar with this, which is called as auto-regressive. So auto stands for self and regression stands for that you're trying to estimate that causal relationship. So this is an example of auto-regressive model of, let's say, order n. What it says is when you have an auto-regressive model, what you're doing is you're simply running a regression of the current variable on all its previous lags, which you determine that on what previous period lags it depend, for which we have different techniques which we'll talk about later. But as far as this equation or this equation is concerned, this equation is an example of what is called as AR model or auto-regressive model, whereby you're trying to find out the value of an independent variable, which is a time series variable, as a function of the values of the one period lag variable that it takes and the 2 period lag value that it takes. And you automatically understand that these previous lags are also attached with or also multiplied with this what we call as the coefficients. So yt minus 1, that is one period lag value of y, has a certain influence. जैसे हम linear regression में interpret करते थे beta naught beta 1 को, in the same manner we'll interpret these coefficients here as well. So this a1 gives us the influence of yt minus 1 on yt. Similarly, and these are the partial influences, this a2 gives us the partial influence of yt minus 2 on yt, keeping in control the value of yt minus 1. And if you have n period such lag, it is an example which is called as ARN model. If you have a model which you simply write it as AT is equal to A naught Y1 plus the term that I have asked you to ignore for the timing, let me just write it in the bracket over here. So this becomes an example of what is called as AR1 model. Now,
sir,
yeah.
Could you please define the coefficients again?
Yeah, these coefficients are the same thing, the way we had interpreted in the linear regression model. जो beta naught, beta 1, beta 2 क्या बताता था? So instead of x's on the independent variable side, now, so इसका logic पहले समझो, interpretation अपने आप clear हो जाएगा. What we are saying is, you see, I have 50 years data of GDP on India, and let's say I want to forecast the value of GDP for the next 5 years. So apart from these 50 observations that I have on GDP of India, I do not have anything else. And I wish to forecast the value of future GDP for the next 5 years, considering the fact that today's value of GDP can be expressed or can be estimated as some function of previous values of India's GDP. And by various technique, I come to find out that only even if we have just 2-period lag GDP value of India or Indian GDP, I can easily forecast the current value of GDP. So what I'm saying that all the previous lags of GDP of India, it does not matter to me a lot. If I just have 2 previous period lags of GDP of India, I can easily get the current value of GDP. So in that sense, this A1, A2, they are called as, simply, they just determine the influence of these lagged values of the variable on the current value. That is, if you keep YT minus, that is, if you have the second period lag explicitly mentioned in the model, this A1 will tell you that in control of this or in presence of this 2-period lag value, how much influence or how much YT minus 1 influences the movement in YT, that is current value of Y. Similarly, A2 will tell you in the presence of 1-period lag, how much influence the 2-period lag values of the independent variable has on the movement on the current value. So in that sense, this A1 and A2, they are nothing but the coefficients, and the coefficient in the sense that they tell you the partial influence of each of these lagged values on the dependent variable. Is this clear?
So, sir, it means they are like weights.
Yeah, they are like weights. They are weights exactly.
Okay,
Yeah.
sir, got it. Thank you.
So अगर इस example में आप simply यहाँ पे लिखो 0.3, 0.7. So what it says that the 30% of movement in Y is explained by 1-period lag in the presence of 2nd-period lag. Similarly, 70% of movement in Y is explained by 2nd-period lag in presence of the 1st-period lag. ठीक है?
Yes, sir.
Okay, all right. So ये point याद रखिएगा, and I'm just introducing all these things. We have not talked about anything, stationarity, stability, and all, anything like that. Now let us discuss about this term xt. And in order to discuss this xt, let us discuss very important term which are called as white noise terms. What are white noise? Anyone?
Sir, excess data which is of not much importance.
Okay. What is a white noise process? Neil?
Sir, I'm not exactly sure, but basically you introduce noise or you introduce some variation to get certain results.
Mm-hmm.
So is it the correlation between different time bands?
No. Haven't you heard this term called white noise error terms? जो हमने sorry. ये जो मेरा एरर है वहां पे, इसके क्या क्या assumptions हमने लिए थे?
the mean is 0 and a constant variance.
Mean is 0, variance constant, and
Normally distributed.
normally distributed
It does not depend on X.
okay,
Co-
that is
correlation
there.
between correlation between X and mu in the long run is 0.
Perfect. So we also write it as, right? Such kind of residuals are generally termed as white noise terms or white noise residuals. When you add the assumption of normality, they become Gaussian white noise terms or Gaussian distribution. Same thing when we talk in the terms of time. So यहाँ पे UI हमने क्यों लिखा था? Because this is a cross-sectional observation. U1, that is error term of the first observation. U2, error term of the second observation. U3, error term of the third observation, and so on till nth observation. जब हम टाइम सीरीज की बात करेंगे तो यहाँ पे सबस्क्रिप्ट T हो जाएगा. So if I denote a white noise residual in time series, let's say by epsilon, and let me call it as ET. So a sequence, since we are dealing with time series or a sequence of equally spaced value. So a sequence ET is a white noise process. Sequence ET is a white noise process if all the assumptions that we had seen above, all the assumptions will imply if each value in the sequence, जैसे हमने बोला था expected value of UI condition on X is 0. So what did we say here? U1 has a mean 0, U2 has a mean 0, U3 has a mean 0, and so on and so forth. Similarly, if each value in this sequence, so epsilon 1, epsilon 2, epsilon 3, epsilon 4, and so on and so forth, all such value in this sequence has a mean of 0, has a constant variance, and is uncorrelated with all other realizations, that is with all other values in its sequence. So formally in statistical notation, since we are talking about these random variables, so I can denote mean by expectation operator. So a sequence epsilon ET is a white noise process if expected value of ET is equal to expected value of ET minus 1 is equal to 0, first condition. Second condition is the variance of each of the a constant, let us call it a sigma square over here. And the third term that we'll have is what it will be?
0, sir.
Correct. So a sequence epsilon t is a white noise process if the mean of each of the value in that sequence is 0, the variance is constant, and they are not also correlated with each other. So this xt, which I had written in this linear difference equation, this xt is just or you can say this xt gets formed by a special combination of these white noise process. So what I say here is that this xt sequence is a sequence which gets formed by combination of these white noise error terms. So I write it as and when you form xt as a sequence of these white noise terms or white noise process, this is called as moving average. सेम इंटरप्रिटेशन ओवर हियर. यहां पे हम क्या बोल रहे हैं कि ये जो कोई वेरिएबल x है ये अपने लैग वैल्यू पे डिपेंड नहीं करता है. इट डिपेंड्स ऑन इट्स करंट एंड प्रीवियस डिस्टर्बेंसेस, where the influence of these previous and current previous disturbances gets measured by this coefficient which is called your betas. So in the same sense जैसे हमने a0, a1, a2 लिखा था, in the same sense these betas are also constants, and here these are the individual elements of the sequence. Now this xt sometimes is also referred to as forcing process. Just get this term. We are not going to talk much about it. So now if I combine this, here, and write it as and so and if I now expand this, so let me say that here you only take, or you say there are no previous lags which influences the current value of y. So in that case, I say that I is equal to 0 and all other coefficients are also 0. And let's say you take here lag 1. So what I'm saying is that yt is equal to a0. I just take lag 1, so I'll write it as a1 yt minus 1. And here what I'm saying that all these coefficients which are there for t minus I, where I say that there no such coefficients have any impact on the current value of y, and assuming that beta naught is equal to beta naught is equal to 1, and all other coefficients beta 1, beta 2 and so on and so forth are 0. So in that case this term will take value epsilon t. So this becomes an example of AR1 model. Now instead of saying that only, so what I'm saying here is that your current value of y is only dependent on the one period lag value of its own lag value and the current disturbance term. Now instead of here, let us say take one lag as well, that is current value of y just does not only depend upon the current disturbance term, but it also gets influenced by what happened yesterday or last year or last month or last quarter. In that case, and let us say that you take beta, so in that case this term can be thought as beta naught epsilon t plus beta 1 epsilon t minus 1. Just for the time being, let us assume this beta naught to be 1. So now this will become so this part is your AR process. Now this is called your moving average of order 1.
So just a doubt.
Yeah.
Given the fact that we have mentioned that it will be influenced by one more term, shouldn't we have an A2 y t minus 2?
No, I'm saying, Neil, कि सिर्फ previous lag y को influence करता है, but y also gets influenced by not only current period's error term, but it also gets influenced by what happened yesterday's error. So in that case, I'm taking the coefficient from that is y just does not only depend on epsilon t, it also depends on epsilon t minus 1.
All right, sir.
Okay? So when you have a model which is estimated like this, they are called as ARMA process. अब इसी को मैं पूरा generalize करूं, guys, I'm just introducing these terms. I have not talked about anything yet. I'm just telling you how do we exactly understand these AR, ARMA, and so on and so forth. We'll talk about estimation of these models in.
Sir, I'm actually not clear on what Neil asked actually. Why, like, if we are adding one extra term in the error part, then why t minus 2 should also come, right? I'm not getting why.
Forcing process is this, no? इसको आप एक्सपैंड करो तो कैसे होगा? बीटा नॉट एप्सिलॉन टी, बीटा 1 एप्सिलॉन टी माइनस 1, बीटा 2 एप्सिलॉन टी माइनस 2, and so on and so forth. What I'm saying is that instead of epsilon t minus 1 also influences y. समझ में आई बात?
Okay, so basically दोनों के लिए we are taking अलग-अलग things. Like for that, for the first part, we are saying that only the t minus 1 influences, and for the second part, we are saying that only current period influences yt.
No. All I'm saying is, you see, this y is a combination of these two terms. ठीक है? Combination क्या बोलता है कि y gets explained by its, so yt minus 1 here is the lag value of y, whereas et minus 1 is the error that existed in period t minus 1. You understand this? So from this, what I'm saying, or what we intend to say over here is that y just does not only depend on its one period lag, but it also depends on the lag value of its disturbance term as well. नहीं आया समझ में?
Okay, sir, understood.
हाँ. All right. So अगर if you now expand the general term, so let me write the linear difference equation again. So an example of an AR1 model will be, AR1 means kya? I am regressing the current value of y only on its lagged value and the current disturbance term and nothing else. So from here I'll take I is equal to 1, and from here I'll take only the current term, that is ET, that is I'll take I is equal to 0. So I can write this as if I'm talking about AR1 MA1 process, then it becomes, so I'll take one lag from both the sequence. If I'm talking about AR2 process, then I'm taking lag and similarly if I'm talking about AR2 MA1 process, then yahan pe I'll add. If I'm talking AR2 MA2 process, then apart from this I'll also add. Is this clear till here?
Sir,
हाँ जी. Yeah.
I didn't get this ARMA part.
बताओ कहाँ पे?
This ARMA part, what's the significance of it? Why are we basically there's the ARMA thing? मुझे पूरा समझ नहीं आया कि हम क्या कर रहे हैं इसमें exactly.
Okay, just tell me what do you understand by this?
Basically that the current period value is dependent upon the previous year and its error term too.
It's current error term.
Sorry, current error term.
ठीक है, अब इसको एक्सप्लेन करो.
It's dependent upon, along with the above part, it's dependent upon the previous error term, previous period error term.
So this ET minus 1 also has an influence on Y. एक प्रैक्टिकल एग्जांपल लेके ये देखो, सपोज यू आर टॉकिंग अबाउट क्वार्टरली जीडीपी ऑफ इंडिया एंड देन यू से दैट जिस क्वार्टर में डिमोनेटाइजेशन अकर हुआ उस क्वार्टर का जो रेसिडुअल है, उस क्वार्टर का जो एरर टर्म है, वो आज के जीडीपी को इन्फ्लुएंस करता है. In that case, so apart from its own lagged value, the current movement in the GDP of India also gets influenced by what had happened in the quarter when demonetization occurred. In that case, what you're dealing with is your ARMA process. That is, not only it is explained by its own movement in the lagged value, it is also getting explained by the residuals of that period, and it influences Y. It influences today's value. So this part is called your moving average part. This part is called your autoregressive part. So what we are saying that if I'm running a model like this, if I'm running a model to estimate or predict the value of Y, which is a time series object, what I'm saying here is that the current value of Y just cannot only be explained by its own lagged value, but also its previous residue. That ये ET minus 1 कब का होगा? ये ET minus 1 previous lag का. So if you're talking about daily data, let's say you're talking about daily stock price data, and what you say is that जो आज का stock price है, it just not only depends on the stock price that was yesterday, but also the disturbances of yesterday influences today's stock price. Is this clear?
Yes, sir.
नहीं होगा तो फिर से I'll deal with. But this is what we should interpret when we see this moving average term.
Sir,
हाँ जी.
in the AR1 model, the beta 1 is always assumed to be 1.
कहाँ पे?
In the AR1 model,
हाँ जी.
1 is always assumed to be 1.
This beta 1, this beta not?
Yes, sir.
Yeah. Why? So why it is? It's not generally. It's a normalization technique. What it says is that ये जो beta naught है. So what it says is that the current error term has an influence on Y or the current period Y, but all other coefficients of this moving average process are equal to 0. So this is just you can say a normalization process where we assume or where we normalize this beta not equal 1. इसका एक restriction है why we keep it to be equal to 1, because you know that's how we derive this forcing process. But just for our understanding, for the time being, you can think that it is generally assumed to be equal to 1.
Sir, it has an interpretation like the current error term influences the Y term 100%.
No. Normalization. This so the coefficient here is not equal to 1. This is normalized. 100% को आप ऐसे समझो कि जो Y है, जो current value of Y है, apart from this getting explained by this lagged value, all other movements in y is contained in this residual term. It should not be understood in that way, the coefficient ke term mein.
Could you repeat that statement, the previous statement?
Yeah, what this ET, which has a coefficient 1, it should be understood in a sense that apart from the movement which is explained by the lagged value of y, rest all other movements are contained in this residual term. So इसको coefficient की तरह please do not interpret.
So I don't get it. Why are we making this normalization?
Normalization इसलिए यहाँ पे how do I tell you? एक second. What generally why do we keep or this forcing process? So what we say when we say here, when we write like this, that beta not equal and rest all other coefficients are 0. So in that sense, the forcing process, the term that we obtain from this forcing process, it only says that we are only obtaining the current residual or current period error term and nothing else. It's only when we have more than one period lag, that's where we start talking about the coefficients of this, coefficient of this forcing process. So when you have moving average of order 1, in that case, beta naught, beta 1, moving average of order 2, in that case, beta naught, beta 1, beta 2. So just for the time being, just take this as given that when we have an AR1 process, the only term that we take out of this forcing process is the ET term, that is epsilon t, that is the current period error term. And rest all other coefficients are assumed to be 0. When we are talking about these, moving average processes. So after the current term, so if you can actually see this beta I, which we say that beta not equal to 1, what it says that the I is equal to 0 means there is no lag. So after you're talking about lag in the forcing process, in that sense, from that point onward, you start taking the coefficients also. So in that sense, this normalization works. When we are not taking any lag from the forcing process, generally we take that epsilon t and we call it as AR1 model. The moment we start taking the lags from the forcing process, that's where the coefficient starts. और इसका एक और logic यही है कि when you do not take any lag out of the forcing process, you generally take that coefficient or you generally normalize that coefficient equal to 1. When you are taking the lags out of this forcing process, then the coefficients have their own value depending on the various stationarity and stability restrictions that will have on the model. So just for the time being, इसको आप ऐसे समझो कि when we are talking about an AR1 model, what we are generally saying is that we do not have a moving average term in this, and that's why we simply take the current error term. When you have more than lags, then you start taking the coefficients out of this forcing process, and these come with their own magnitudes. So this is what, just for the time, you can think this term to be like.
Okay, sir.
Sir, how do we get the white noise if we have a given data? So how do you find the white noise that epsilon t?
You see, you generally do not get white noise in pure practice. So one thing you see, even when we talk about linear regression, how do we guarantee this assumptions? No such guarantee, right?
Sir, I mean, in the regression model, we used to subtract the actual values from the estimated values, and we get the error terms.
That is for the sample.
Yes, sir.
है ना? वो sample residuals है.
Yes, residuals.
हाँ.
So that is not the absolute terms here. It's
no, you see, so even when we did that, we got EI, not UI. And this EI was an estimate of UI, assuming all the assumptions are true. In the same manner, so ET can still be obtained like this over here. But this ET will be for this sample. So in true sense, white noise error term actually obtain karna, you can run a simulation program and you can have all this, well-behaved normal distribution of where you can simply generate a sequence of random observations having mean, zero, constant variance, and so on and so forth. But when we write such model, generally the error terms are assumed to behave like this. It is only when the error term do not behave like this, that's why we have certain restrictions, we impose certain stationarity restrictions, which is what we'll study when we move ahead. But the process will remain same. You can get ET by, YT minus this term, and that's how the way we obtain the linear regression as well. But you have to understand that this will be, or एक और जो problem as far as time series is concerned is that you have one such recorded observation for each time period. In cross section, you can generate that simulation. So when we write, even when we talk about that linear regression function, so what we say that for one x1 we can have, let's say, normally distributed y values, but no such thing occur in time series. For one time period, you have one value, you have one realization. For the next time period, you have other realization, and so on and so forth. So this kind of replication, or the comfort of replication that we have had in cross-sectional data, we do not generally have in that in time series. So generally, जैसे हम UT के लिए ET को estimate करते थे, in the same manner, such kind of thing, it will be hard for us to replicate here. And this epsilon t is just there to tell you that this is how the current error term or current period error term as far as this y is concerned should behave. If it does not behave in that manner, then you will be facing a problem. So, and to begin with, I mentioned that this is one particular example of a difference equation, that to a discrete time series process. Your actual time series need not have a white noise error term. Your error term might be, or it might have a non-constant variance. In that case, you have different things like conditional heteroscedasticity. So there are various modifications done to the original model. So as a benchmark, you can think of this as the population regression function the way we wrote. It is only when there is a problem associated with this error term, that's where you have different models that you can run.
So,
Haji.
So the white noise is nothing but the error term, including the lag values. Or is there some difference between, or just a terminology difference?
No, it's the same thing. The residuals जो हमने linear regression में assume किया था, same thing है यहाँ पे. Only thing that these are the sequence of observations for across time periods. So those were across observations. These are a sequence of values separated by that equally spaced time.
Okay, sir. Sir, then why is it regarded as the moving average? Like moving average is something different, right?
Moving
like,
average.
What is the link of this with the moving average?
You see,
like we generally calculate 1 year moving average or 4 months moving average. Like in time series, we used to calculate this.
Yeah. So what do you do in moving average? What exactly happened in moving average? So if I write YT is equal to what does it mean over here? How do we interpret this equation?
So basically the like error terms of the two last time period is also affecting YT, like current period error term plus two previous period.
So this is exactly a process which is your moving average 2 process. So when you actually undertake an exercise of moving average process of smoothing a time series, actually you do this. You simply take the previous 2 error term along with the coefficients, jo bhi, the values of the coefficient that we have, and you simply add them up. This is how you smooth the time series to obtain a trend. And that's why it is called a moving average process. अब इसको और थोड़ा better समझना है. Suppose, just for the time being, suppose you play a game and let's say it's a coin toss game and you win ₹1 for head and you lose ₹1 for tail. So this is a game that you're playing. So let us say denote the outcome that we generate or that we get on any toss T. Let me call it as ET. So ET can be either +1 or it can be -1, right? And now this is the game that you have been playing, let's say, and now at this point of time, that is at toss T, you want to find out what is your average payoff on the last 4 tosses. How do you calculate that?
So
Yeah.
basically we have to see the past events, like past and
But past, यहाँ पे देखो ET, ET -1, ET -2, ET -3. These are the last 4 tosses at the current time, right?
yes sir.
हर एक का आउटकम 2 ही होगा, या तो +1 या -1, +1 या -1, +1 या -1.
Yes sir.
Right? In that case, either one, so it will be 1/4 times ET plus 1/4 times ET -1, जो भी आउटकम था लास्ट टॉस में, प्लस 1/4 टाइम्स ET -2, जो भी आउटकम था सेकेंड लास्ट टॉस में, प्लस this is how you will calculate your average payoff in this game. Either +1 or -1 times that outcome, +1 -1 outcome, +1 -1 +1 -1 times that outcome.
Yes sir.
ठीक है. So ये basically आपने क्या किया है यहाँ पे calculate? Average payoff is explained in this term. In this case, your beta, अगर मैं forcing process से compare करूं, in this case your beta is 0.25. So what is happening here is now that if on one particular toss outcome you have, let's say, +1, then it will go up by 0.25. If one particular outcome, if you have -1, it will go down by -0.25 and so on and so forth. So last 4 जो एवरेज पे ऑफ था आपका, that you get by accumulating all the previous outcomes along with their respective chances. Moving average simply से मान लो सपोज तुम्हें विराट कोहली का लास्ट 10 इनिंग्स का स्कोर दिया गया है, राइट? So you have 10, individual scores of Virat Kohli's past, 10 innings, and now you're asked to find out the moving average of this score for, of order 3. So what you do, you take, 3 individual scores, you find out the average, then you take the next 3 sequence of moving average scores, you find out the average, and so on and so forth. That's how you generate a sequence which is based like this. So moving average process is nothing but the sequence that you generate out of this forcing process. Where the coefficients which are attached with, so if you're calculating moving average of order 2 or of order 3 or of order 4, what you're simply doing is, if it of order 2, you're calculating that, or you're summing up, you're finding the average of the 2 sequenced observations. If it is of order 4, you're finding out the average of 4 sequenced observations, and so on and so forth. You progress. So moving average basically gives you an idea of trend, whether you're going up or you're going down. So if in the coin toss example, if in the last 4 tosses I have got, let's say tail, and I have lost 1 rupees in each of the toss. So my average will go down by minus 2.5, minus 2.5, minus 2.5, minus 2.5. So it will give me a downward trend. Instead, let's say I have won all the tosses. It will give me an upward trend. So moving average basically is based on this concept of where what you do is you take, the current observation along with all the observations or all the outcomes that existed in the previous period, scaled up or scaled down by their respective coefficients. And this is precisely a moving average process. ठीक है? तो ये moving average इसलिए क्योंकि what it does, it gives you a trend. It gives you either upward trend or downward trend. Because what it does is it it's attached to them. So, and why it is called a moving average, again, you can think from the conditional regression example that we had got. When we find out why like this, what we are generally saying is that this is the expected value of y condition on all the previous outcomes, right? Is this clear? This is expected, that is conditional y on all the x's or all the outcomes that we have got.
Yes, sir.
And that's why it is called as moving average. So either it gives you an upward trend or downward trend, depending on how the outcomes on the previous observations have gone ahead.
So the interpretations of beta 1 and beta 2 are just the same like we did in linear regression?
Correct.
Sir?
Haji.
Sir, on what basis we can decide which lag is to be taken in while autocorrelation?
See, yes. we have not talked about that at all. We have just introduced these terms. There are terms like which will come across ACF, PACF से हम decide करते हैं कि कितना AR lag होना चाहिए, कितना MA lag होना चाहिए. All that we have just done now is to introduce कि how do we exactly understand what is an AR and what is an MA process.
Okay. And sir, as you earlier said about no autocorrelation, so is it possible that zero autocorrelation lag while in practical it is possible?
Yeah, definitely.
Okay. And sir, one thing more, that sir earlier you talked about white noise process. So
yeah,
sir, is it necessary that always in all the prediction white noise process will be there in the model?
No, it's not necessary. But when, see, a second, let me write this down. Just for the timing, I've just taken an ARN model. This is a model. This is a model to talk about or to estimate or to predict or to forecast the value of a time series variable. So since ये मॉडल है, इसलिए ये इसका assumption है, जैसे लीनियर रिग्रेशन मॉडल था,
हाँ जी,
है ना? लीनियर रिग्रेशन मॉडल में we assume the errors to be like that. अभी थोड़ी देर पहले there was the similar doubt.
Yes, sir.
So we assumed our error term to behave like that. Similarly, this is an AR model, just ARN model. So ARN model is for what? हमारे पास एक टाइम सीरीज वेरिएबल आया, मेरे पास एक डेटा है, उस डेटा पे मैंने एनालाइज किया. आफ्टर एनालिसिस आई हैव डिसाइडेड दैट आई नीड टू रन और आई नीड टू हैव एन AR मॉडल फॉर दिस. सो वो आपका एक मॉडल है, एंड दैट मॉडल रेस्ट ऑन सर्टेन assumptions, and that's why the error terms or the current error terms which are attached to that AR model are assumed to be behaving as a white noise process.
Okay, sir.
Is this clear?
Yes, sir.
Shall I go ahead?
Yes, sir.
Okay, all right. So after having understood this, let us take this forcing process, in a bit more detail. Let me, instead of writing infinity, let me take it as Q lag. So now one thing that you should understand here is that though this epsilon t themselves are a sequence of white noise process, but it is not necessarily true that this xt sequence will also be a white noise process. I'll repeat. Though this epsilon or this sequence of observations are a white noise process in themselves, but it is not necessarily true that the xt sequence, which is formed by this epsilon t sequence, need be a white noise process. And why so? Let us, just take an MA1 model. So if I'm taking an MA1 process instead of model, let me write it as MA1 process. So moving average 1 process. So I can write this as, and again, let us take beta not equal 1, beta 1, 0.5. These are the values that I've taken. So my xt will look like, it will be epsilon t plus 0.5 times epsilon t minus 1. So in order for xt to be a white noise process, it must satisfy 3 conditions. Its mean should be 0. Its variance should be a constant, and it should not be correlated with other realizations. So I can easily find out mean. If I take expected value of xt, it will be expected value of epsilon t plus 0.8 minus 1. And you can easily verify expected value of epsilon t will be 0. Again, this is a constant. 0.5 times expected value of the epsilon t minus 1 will be 0. So it is 0. Again, in order to talk about variance of xt, I can easily find it out as variance of et plus 0.5 et minus 1. So variance of et squared is sigma squared. Variance of et minus 1 will be 0.5 ka square times that sigma square. So 0.5 square is 0.25. So this will be 1.25 sigma square, which is again a constant. So variance is a constant, mean is constant. Let us find the third condition, which is the correlation. So let me write it as xt and xt minus 1 ka. So I can write this as
sir, we are just taking a an example that it is 0.5?
Yeah. It's an example. Yeah. Now, if you calculate this covariance term, so ET minus 1, it should be 0. ET minus 1, ET minus 2 term will be there. Then you have ET minus 1, ET minus 1, which will be variance of ET minus 1, which is nothing but sigma square. So the only term that will be left is this term. That is 0.5 ET minus 1 times ET minus 1. So I can write it as 0.5 sigma square. Now this is not equal to 0. Which tells you, or which gives you an indication that though xt is made up of these white noise sequence or white noise variables, but it is not necessarily true that the sequence which is formed out of this white noise process will also be a white noise. And इसका एक general hard and fast rule है that this xt or this moving average sequence will not be a white noise if 2 or more than 2 beta i's differ from 0. So get this general rule in mind that though xt is formed out of these white noise sequence, but if there are 2 or more than 2 of the coefficients which are differing from 0, in that case the sequence generated out of these white noise process will not be a white noise process itself.
So could you please repeat this?
Yeah.
If the beta i's are not, I'm so sorry.
If 2 or more than 2 beta i's in this forcing process, they differ from 0, then the sequence xt will not be a white noise process.
So through this example, how did we prove this statement?
White noise process के लिए क्या चाहिए हमें? White noise process के लिए में चाहिए 2 or more than 2 beta i's differ from 0, right?
Yes, sir.
In this case, I have 2 betas which differ from 0, which is not 0.
Okay.
So
Haji.
you are saying that epsilon follows all the white noise like conditions, but this xt terms doesn't.
Correct.
I got it. How you proved that, but it's like not like theoretically it's not sounding correct.
But why?
Because xt is the combination of all the epsilons.
But it's a linear combination, right? It's a linear combination. So you have to understand that these epsilons, they themselves have mean variance or autocovariance is 0. But when they are attached with this weight, so when you calculate the covariance term, that need not be 0.
Okay.
मीन वेरिएंस हमेशा आपको कांस्टेंट और 0 आएगा, बट कोवेरियंस टर्म में देयर इज अ क्रॉस प्रोडक्ट टर्म, and that cross product term, if it is if the betas are significant, if the betas are not 0, that cross product term will be there and that will be non-zero. And that is why the sequence formed out of white noise process necessarily need not be a white noise itself.
Okay, sir.
So could you just scroll down for a second?
Haji. Yeah.
So down, not up. Condition 3.
Sir.
Haji.
अभी जो आपने बोला कि ये सीक्वेंस जो व्हाइट नॉइज का बनेगा वो जरूरी नहीं कि वो भी व्हाइट नॉइज हो
हाँ जी,
बनेगा।
हाँ जी।
तो इसका मतलब जो सीक्वेंस बनेगा वो जो डिपेंडेंट वेरिएबल होगा उसको एक्सप्लेन करेगा काइंड ऑफ।
नहीं समझ में नहीं आया, क्या बोला आपने?
सर अगर वो सीक्वेंस अगर बनेगा जो अगर हमने यहाँ पे एक्स जो लिया है
करेक्ट,
वो अगर व्हाइट नॉइज नहीं हुआ दैट मीन वो भी एक एक्सप्लेनेटरी वेरिएबल हो जाएगा क्या?
correct, yeah. That's why moving average models or process are estimated or made alongside AR model. So basically देखो logic क्या है कि जहां पे सिर्फ AR process not only works, that is you're not able to truly explain the dependent variable in the terms of its lag only, but also residuals are also needed. That is जो previous error term में या previous term में जो भी कुछ residuals or errors are also shocks. It's like you can take this example कि suppose Maharashtra से बिहार onion जा रहा था and let's say two of the trucks meet with an accident and that's why supply of onion for the next few days is disturbed. And since supply is less, the price of onion has gone up. Now, if I'm running or if I'm trying to estimate a model to find out the price of onion, and if I just run a model, taking that price of onion to be dependent on its own lagged one previous or two previous, but that price of onion also gets influenced by what actually happened 1 week ago or 5 days ago. In that case, the shock that occurred in the fifth period lag should also be, explicitly included in the model. And this is what precisely the moving average term does. So explicitly counting those, shocks that occurred in the previous period, explicitly in the model, it kind of works as an explanatory variable, to understand how the current value of the variable moves. So when you have this moving average sequence also attached with the AR, in that case you are running that ARMA model, and that tells you that Y just does not depend on its own lag. It also depends on the lag disturbances values as well. So in that case, they become the explanatory variables. Is this clear till here?
Yes, sir.
Yes, sir.
Okay, all right. So let me just rewrite what we had talked about till here. So if I have to write or if I have to talk about an ARP MAQ process or model, how am I writing it? YT right? So this becomes your ARMA PQ process. यहां तक बात क्लियर है?
Yes, sir.
All right. So in notations and terminology को ध्यान याद रखिएगा. अभी yeah.
Won't the epsilon start from T and not T minus I?
कहाँ पे? हाँ. Yeah. In the forcing process.
And so shouldn't there be an AI term in the AR part?
Yeah, definitely. It should be.
So it should be T minus I.
Yeah. ठीक है? Shall we go ahead?
Sir, can we conclude for this session for now?
Just
Yes,
just give me 2 minutes to introduce one term, then we can proceed at 3.
Okay, sir.
2 minutes chalega?
Yes, sir.
Yeah. All right. So these the examples that we just now talked about, these AR process, MA process. So these are processes, these are models, these are these are our assumptions, or these are our indications about the time series variables that we have had in, or that we have in front of us. But जितने भी मॉडल्स हमने भी देखे, whether it's AR, whether it's MA or ARMA, in order for these models to be estimated or for these models to be run, there is this very, very important concept that must be checked, which is called as stationarity. So even these models must be stationary. अगर ये stationary नहीं रहेंगे, then these models are good for nothing. अब stationarity क्यों इतना necessary है time series में, उसको just let me explain this and then we can break. You see, a time series process is called a stationary process. A time series process, or a stochastic process, is called a stationary process if its mean and variance are constant across time. I'll repeat this point. A stochastic process is called a stationary process if the mean and variance of the series remains constant across time. Now, what exactly we mean by this? Let me just explain this and then we can break. You see, when you write this sequence YT, and this sequence is what? This sequence is the, the set of observations which are linked across time. So you have y1, y2, y3, y4, y5, y minus 1, y0, y minus 2, y minus 3, and so on and so forth. And if you want to talk about, or if you, on the basis of the observations, on the basis of the data points that you have in front of you, and since they are linked across time, it means that they are jointly distributed as well. And the moment these, we come across this joint distribution, on the basis of this jointly distributed stochastic variables which are linked across time, if you want to predict, if you want to forecast anything ahead, so it is necessary that for the time being which you are observing, because the data is only limited for you for that time period. If you have 50 years GDP data, you have 50 such variables which are linked across time. So you have a jointly distributed 50 such stochastic variables. And if they're jointly distributed, they'll have a nice probability distribution with them. And if you have a probability distribution, you will have a mean, you have variance, you have skewness, kurtosis, and so on, higher moments of distribution. And on the basis of this 50 observations that we have in front of us, if we want to predict anything ahead, so prediction is based on the mean and variance. This is how you form your confidence intervals. This is how you form your prediction. And if that mean or variance do not remain constant for the time period you are forecasting, then your forecast and your prediction goes for a toss. And it is precisely for this reason why we need to be very certain that the time series variable that we are dealing with is stationary in nature. Now, more or less, almost all the time series variables that we come across, they are mostly non-stationary. Their mean is not constant. Their variance is not constant. So the first task that as a researcher, whenever we come across time series observation, we do is to perform the stationarity tests. Now you should understand, since we are estimating, or since we are running a model to estimate y on the basis of ARMA or AR process or MA process, we need to also make sure that the processes that we are estimating should be stationary as well. Because ultimately, जो भी आप model बनाओगे उसके basis पे आप predict करोगे, and if the process itself is non-stationary, your prediction does not hold true. And that's why stationarity is one of the single most important concept as far as time series is concerned. So in the next session, we'll start with here. We'll talk about the weakly stationary process, that is also called as covariance stationary process. And then we go ahead and talk about certain tests of stationarity. How do we actually conduct these tests for stationarity? And then we take one of the example from the book that I had sent you in the morning to precisely write exactly some of the R command for time series on R. So let's take a break. We meet at 3, right?
Yes, sir.
All right. So at 3, we'll start with the covariance stationarity and ahead. Thank you.
So,
Yeah.
yes, sir. Stationarity is just based on the independent variables or all the variables that are in the models?
Stationarity is for the variable that you have. That इस केस में independent variable क्या है आपका? If you're running an AR model, if you're running an MA model, AR model run कर रहे हो, it means, see, तुम्हारे पास variable सिर्फ एक ही है. Number of observations जो है आपके पास, they are for different time period.
Yes, sir.
है ना? तो variable, independent variable बोलो, dependent variable बोलो, it does not, change a lot of things. All we need is the variable that we have in front of us must be stationary. Stationary का मतलब कि उसका mean और variance constant होना चाहिए. अगर वो, you see, even in linear regression, हम prediction जो भी formula लिखते थे, confidence interval जो भी लिखते थे, we assume there. Since we are dealing with cross section, we make sure that that the conditional mean and conditional variance remains constant, which is what we again make sure in time series observations as well, which are called as stationarity assumptions of time series, which is what we'll talk about in the next session.
Okay, sir. Thank you.
Yeah. All right, then we meet at 3.
Yes, sir. Thank you.